px comma 7. So the difference here is they're giving you the y value. That's the only difference here. So you're going to need to calculate the x value. You're going to have to find the x value. Well, here I have 7 equals radical x, and so I'm going to square both sides to solve for x. And so x is equal to 49. Okay, that was the trick to this question. Okay, so I'll say that again. I have 7 equals root x, and if you're solving for x then, you have to get rid of that radical, so you're squaring both sides. So x is equal to 49. And then you're subbing into your regular formula to find the slope of the tangent. And I have 40, radical 49 to base minus 7, that's my y value, all over h. And I notice that if I sub in 0, well, then I have 0 over 0. I can't have that. And so I realize that I have to use the conjugate method to solve. So I multiply by root 49 plus h plus 7 over root 49 plus h plus 7. And I expand. And again, guys, look, we do not expand that denominator because the whole reason we're doing this is to cancel out that. So we cancel it out, and you're left with this. And now you can sub in 0, and we get 1 over 14. Are there any questions? How'd you guys do with this? That's good. Excellent. At home, how did you guys do? How did you guys do at home? Good? Good, Ryan. Anyone else? Anyone else there?
Miss, can you show the last page again?
Yeah. Oh, hold on. Where do you want me to go?
Just the bottom.
Bottom? You good?
Okay, thank you.
Is that good?
Yep.
So check your mistakes, right? And be careful. Calculus is not difficult. The problem with calculus is it's meticulous. So there's a lot of algebra, right? It's very much algebra based. And so you have to be careful with your negatives. You've got to be careful with your exponent laws. You've got to be careful with all the little errors that can happen on a test, right?
Miss,
Yes.
we can't hear you very well. There's a lot of background noise.
There's a lot of background noise.
Yeah.
Is everyone finding that?
Yeah, it's still a little fizzy and like we can't hear you that clearly.
Yeah, a little bit.
Okay, unfortunately, I don't think there's anything I can do. Let me try unplugging the mic and plugging it in again. As I get closer to the screen, you'll be able to hear me better, but let's try that. Did that help at all with the background noise?
Not really.
Not really. I'm sorry, guys. This is what it is. I apologize. I'm not sure why. But like I said, as I get closer to the screen, it will get better. Okay, are you guys ready to start with today's lesson then? All right, so let's go to 1.4. Does anyone in class need the handout for 1.1? Do they need it or you've already completed it? And 1.5, anybody, or do you guys have it? It's only the first two. No? You have it as well? What I'm gonna do is right now before I forget, I'm gonna do that. Yes, Grandma. We're doing it. Because I already wrote about it. You did? Okay. All right. So, limit of a function. So we watched that video. What did you guys think of the video? It's pretty cute, no? It was cute. It was a good way to visualize what a limit is and what it means. So, when a function f approaches the limit L as x approaches a, we write the limit as x approaches a of f of x equals capital L. That's just what the limit equals, yeah, when we evaluate it. If the left-hand limit, so look how we write that here, as x approaches a from the left, you have a little minus sign there, signifying that it's a left-hand limit, and the right-hand limit, excuse me, so if the left-hand limit equals L, and the right-hand limit equals L, are the same, so we notice they equal the same value, then we say that the limit exists. If the left-hand limit and the right-hand limit don't go to the same place, so they don't equal the same value, then the limit does not exist. Okay, so the limit here exists because both the left-hand limit and the right-hand limit equal. Okay, example 1. Given f of x equals 3 minus x squared, find f at 2. So what do I do to find f at 2? Yeah, you can do it algebraically by subbing in. We have the luxury of having a graph here, so you could even just go to the graph, right? F at 2 means x is equal to 2, and it's right there. So what does it equal? -1. Okay? If you didn't have the graph, then you have to just sub in and find it algebraically. The limit as x approaches 2 from the right-hand side. So I have my little card here. So I want to now approach x equals 2 from the right. When I approach x equals 2 from the right, I'm here. When I approach from the left, I end up in the same place. So here, I can say the limit as x approaches 2 from the right of your function f of x equals -1. The limit as x approaches 2 from the left of f of x also equals -1. And so now I can say that the limit exists and equals -1. Left-hand limit and right-hand limit equal the same thing.
Miss, can you go up for like 1 second?
Sure. How far? Is that good?
Yeah, thank you. That's it.
Yeah, no problem. Okay, evaluate if possible. So I have x squared minus 4 over x minus 2. So when we evaluate limits, we just sub in, right? So I sub in 2. Well, what happens? What happens if I just sub in 2?
The denominator is 0.
Yeah, my denominator 0 is that, right? I got 0 over 0 here. So I'm going to use, I have to find the method, right, to simplify this better. And so by looking at it, you should all see that we're going to factor. So what type of factoring is this? Yep. Difference of squares. And now, I can divide out the x minus 2. And now I can put it. Now, from what you guys know, when you cancel out x minus 2, what does that mean if I wanted to draw out this function? Yeah, there's a hole. So the fact that we canceled out this x minus 2 tells us that there is a hole at x equals 2. So if I wanted to graph this function now, I have to graph x plus 2. So it has a y-intercept of 2, and it has a slope of 1. There's a hole there. That's what this function would look like, yes? And I don't know if you guys have ever retooled, I'm sure you have, but I don't know if you remember, but when you're drawing graphs, if you go right to the end of your graph, you don't need an arrow, because you're going right to the end. So that automatically, we assume that it goes on forever. But if you stop short, like I did over here, I didn't go all the way to -5, you must have an arrow to show. So to be safe, you could just always put it, which is what I did here. I put an arrow on my right-hand side here, as we're after 3, right? When x is greater than 3, when I didn't really need it. So you're not going to lose marks if you have it, so it's better to just put it. Because you will lose marks if you don't have it and use it, right? Okay, so hole at 2. So let's talk about limits now. So if I take this and I approach from the right-hand side, I still end up here. Sorry, approaching 2. I put my hole in the wrong spot, right? Come on, why is nobody telling me? It's got to be there. Oh, that's not good. Sorry guys, hold on. All right, good enough. So we see that there is a hole at 4. But when I approach from the right, I drive my car, I go to 4. And when I approach from the left, I also arrive at 4. So that means my right-hand limit and my left-hand limit are both equal to 4. And so the limit exists. This comes out through the algebra. You see this in the algebra, yeah? But let's note that both limits from the left and from the right both equal 4. And note you would not have to show me this unless I ask for it. Okay, but just for the notes, I'm going to add it in. When we're approaching x equals 2 from the left and from the right, our intended type is 4 for both. Okay, here we have a step function. We want to take the limit as x approaches -2 of this step function. So here, what does this mean? First of all, talk to me about this function. What does this tell me? How is this function defined? Nobody? What is this function telling me? Guys, you have to be able to know how to read these, right? So when I look here, does somebody at home want to help?
So to the right of x equals -2,
Yes?
we use the equation y equals x plus 2.
Okay, good. We're going to use the equation y equals x plus 2 when x is greater than or equal to -2. So let's draw that part of the function first. So again, it's got a y-intercept of 2 and it's got a slope of 1. And I want to throw one. All the way to -2. Now let me ask you this. Should I have a closed circle or an open circle on -2? Good, closed circle, because it equals. Very good. Excellent. Now, what's happening when x is less than -2? When x is smaller than -2, what does y equal? Yes. So remember, guys, this is just f of x equals -1, which is the same as y equals -1. What type of a line is this? Good, it's a horizontal line. So it's a horizontal line at -1. So it's like this. Open circle, closed circle. Yeah, it has to be. You can't have two closed circles, right? You can't have two different values of y for one x. Then it wouldn't be a function. Do you guys remember that? So one of these has to be closed and one has to be open. They couldn't both be closed. And this is the one that is open because it's not equal. All right? And this one. Okay. So now, when we look at this, what do you guys think? Is the limit going to exist? No, the limit is not going to exist. You can see that visually because when I approach from the right and when I approach from the left, I don't end up at the same y value. I end up at different places. So I can visually see that this limit does not exist. Now, we don't want to have to be able to draw graphs every single time just to take limits. So what you need to do in a case like this, because it's a step function, is you have to take the right-hand limit and the left-hand limit. I didn't have to do that for the first example, but for this one I did. So let's take the limit as x approaches -2 from the left. So to find the limit as x approaches -2 from the left, where would I be, which function would I be using? Would I be using x plus 2 or -1? Which one would I be using? Yeah, good, -1. It's already done for me. It equals -1. When I approach 2 from the right, well, that means now I'm using the linear function. I'm following the line. And so it's x plus 2. And because I don't get 0 over 0 here, I have no denominator here at all, I just go ahead and sub in. So I evaluate this limit, which equals 2. Oh, sorry. How come I didn't equal 2? What happened here? Thank you. I wrote 2 here. Thank you. I don't know why I did that. Our x is approaching -2. And this equals 0. There we go. We notice that the left-hand limit is not equal to the right-hand limit, and so therefore the limit overall does not exist. So since the left-hand limit, a little bit of shorthand now, does not equal the right-hand limit, overall, the limit as x approaches -2 of f of x does not exist. Now, what you guys will do, you don't have to write does not exist, you're gonna write D and all in capital. So here I sub in -2 because that's the x value that we're approaching, right? Are there any questions so far? Okay, now. Limit as x approaches 0 of root x. Okay. So here, I can sub in 0. What's the square root of 0? Oh, so my limit 0. What do you guys think? Think that's good? Let's graph it. Let's see. If I can graph it, what are some points on my graph? Okay, 0, 0. What else? 1, 1. And then 4, 2. Beautiful. There's my root function. What do you guys think? Would the limit equal 0? The answer is no. And the reason is, there's no left side. I've got nothing here to approach it. It's not approaching anything from the left. It's only approaching from the right. This limit does not exist. So this is misleading. So be, yeah. So be very, very careful with roots. Now, if I had said to you this, does this limit exist? The limit as x approaches 4 of root x. Does that limit exist? It does. This limit exists because I have a road to follow. I have a road to lead me to 4. And I have a road to lead me to x equals 4 from the right and the left. So therefore, this limit would exist and it equals 2. So be careful. Yeah. I'm sorry? You know what? To prove it, it's as simple as taking a right hand and a left hand limit. Exactly. So since your domain is x is greater than or equal to 0, the limit as x approaches 0 is not exist. Okay? So let's make a note of this. So the limit as x approaches 0 from the left of root x does not exist. Therefore, the limit as x approaches 0 does not exist. You have to have a left hand and a right hand limit. The right hand limit has to equal the left hand limit. Cool? Are there any questions here? Yes. Oh, no, you can just say it. Yeah, you can just say, if I get asked you to evaluate a limit like this, you can just say does not exist. Okay? Good. We're going to talk about continuity, and when we talk about continuity, you're going to learn about the steps. There's certain steps that you must show to prove whether or not a function is continuous. Okay? Yeah. You would just say does not exist. That's all you have to say. Does not exist. D-N-A. Okay? All right. Let's look at D. So here we have another step function. How do I draw it? You guys try to draw it. Try to draw it. Let's see if you guys can figure it out. Okay, help me out. How would I draw this? Okay, good. So what Tammy is saying is that here I have two functions. I have y equals 5 and I have y equals 3. Now these are both horizontal lines. However, y equals 5 only exists at one point when x is equal to 1. So even though it's a horizontal line, it's only happening when x equals 1. And so this is really just the point, 1 comma 5. It's really just this. Now this is a horizontal line going through 3, but it happens everywhere except where x is equal to 1. So there is a hole here. It happens everywhere except. So this is what you have happening here. Okay, guys, what do you think? Does the limit exist, yes or no? What do you think? Turn it around. Yeah, so Lily says yes, because if I approach this from both sides, I follow the road, all roads lead to 3. My left-hand side and my right-hand side both are bringing me to 3. And so what is the actual limit? If we evaluate this limit, what is it? It's 3. Good. It equals 3. And we'll make a little note. Since right-hand limit equals left-hand limit. It's equal 3. Yes, Tina. You have a question? I'm sorry, just one more second. I'm sorry. Okay. A limit, no. No, the limit is 3. The limit of this function, when you follow the graph, it leads you to 3. That is the limit. It's the intended height. It doesn't matter if it actually equals 5. It doesn't matter. When you approach from both sides, it's bringing you to 3. Okay, so be very careful. So this limit exists, and it is 3. Okay? Are there any questions at home? Okay, let's do, yep. Yeah, for that one, what I would show, I would show a left-hand limit and a right-hand limit. Yeah, that's all you would have to show for this one. Left-hand limit, so you could show limit as x approaches 1 from the left and x as it approaches from the right, and in both cases it's 2. Okay? All right. So limit of f of x as x approaches 0. The function is 1 over x. The function is 1 over x. So can I just go ahead and take this limit? What would happen if I just try to take the limit here? Yeah, it's undefined. So what does that mean? Never approaches 0? Or never equals 0? Never equals 0. So what do I have? What do I have on my graph? If I could draw this graph, how would I draw it? So whenever the denominator is 0, what is that? Yeah. There's a vertical asymptote at x equals 0. So let's draw that in. There's my vertical asymptote. From what you guys know of functions, because you guys are familiar with this function, right? Your rational function. What else is happening here? Yeah, there's also a horizontal asymptote. You guys have seen this function in the past. We have a vertical and a horizontal asymptote. So I have a vertical asymptote, x equals 0, horizontal asymptote, y equals 0. We always label our asymptote. Okay, now I want to draw my graph. So you guys can just use the table of values. And in grade 11, you would have been taught to use 3 points when drawing this, yes? Now, because the question here is not asking me to graph, we just want to analyze, I'm okay just doing a quick scan. So if my x value is 1, I can see that my y value is also 1. If my x value is -1, my y value is -1. This is telling me that I'm approaching this way and this way, because we always approach the asymptotes, right? So what this means is my graph gets close to 0, really, really close to 0, but it never equals 0. And I don't have to be any more specific than this because the question is not about graphing. The question is analysis. We want to know what the limit is. So if I follow to find my right-hand limit, I'll use this guy. What's my right-hand limit? What would my right-hand limit equal here?
Positive infinity.
Beautiful. It never ends. This graph goes on forever and ever and ever. So it is approaching positive infinity. Beautiful. So if I take my limit as x approaches 0 from the right of 1 over x, it equals positive infinity. If I take the limit as x approaches 0 from the left, let's see what it equals. Oops. Where does it equal? Yeah, negative infinity. Very good. Are my limits equal? So can this limit exist? The limit does not exist. The intended height of the function is not the same for both limits. It does not exist. So, since the left-hand limit is not equal to the right-hand limit, the limit of x approaches 0 of 1 over x does not exist.
Miss,
Yeah.
how did you find the horizontal asymptote?
So we know, you guys haven't really technically learned how to find the horizontal asymptote in this case, but you guys have learned in the past that when you're dealing with a rational function, it always has a horizontal asymptote at y at somewhere. In this case, it's y equals 0. So let's talk about y. The reason is there any value of x I can ever sub in that will make my y equal 0? Is there such a value? Can you think of a value of x that I could ever sub into that denominator that could make this equal 0?
Infinity?
No. No.
Am I tripping? Is it not negative or positive infinity?
Well, but I'm asking for an x value. Is there an x?
No, there's not.
There's not, and that's why an asymptote exists.
Okay, that makes sense. Yeah.
Yeah. There's no real number that I can ever sub into that to make that that y equal 0. And so therefore we know there's a horizontal asymptote there. Throughout this course, I am going to teach you how we find horizontal asymptotes exactly through limits. You couldn't be taught that in the past because you didn't know limits. So we did it by analysis. Well, no. So we're saying there's a horizontal asymptote here because there's no value I can ever sub in here. There's no x value that will ever make the function equal 0. Y never equals 0. And if y never equals 0, then we know there's an asymptote there. There's a break there. Because y never equals 0. Okay? All right. Let's take a look at this guy. How do I graph this guy? 1 over x squared. So, is the denominator ever 0? That's the first thing we look at. Is the denominator ever 0? What makes this denominator 0? 0 does. And so we have a vertical asymptote at x equals 0. Any other asymptotes with this graph? Any other asymptotes? Good, there's a horizontal one as well. And for the same reason, there's no value of x that I could ever sub in to make this function equal 0. Okay, now again, I want to get a general idea what's happening with this function. So let's just sub in 1. If I sub in 1, what value do I get? Yeah, 1. So that means I know this is happening. We always follow the asymptotes, right? That's what graphs do. It's like a magnet, right? The graph always follows that asymptote. Never touches it, but it always follows it. Okay, so now I'm going to sub in -1. So if I sub in -1, what's my y value? It's +1. I've got 1 over -1 all squared. Okay. Now let's take our limits. I want you. So now, if I approach 0 from the right, what does it equal? Yeah, positive infinity. And if I approach 0 from the left, what does it equal? Positive infinity. Are the limits equal? Do they equal the same thing? The limit exists. The intended height of the function is the same. It's positive infinity. And so therefore, the limit exists.
Yes, you wrote negative infinity.
Oh, I'm sorry. And you don't really need the positive there, right? Infinity is positive. Are there any questions? No? Make sense? Okay, so be careful, guys, with these special cases. This is all you gotta watch out for. Because the rest is easy, right? The rest, when you sub it in, you get 0 over 0. You know that you're either going to factor or you're going to use the conjugate to get your result. But there are certain functions that need analysis. These are that. Okay? So you've got an asymptote involved, or it's a step function. You've got some sort of break in your function. These are the ones you have to watch out for. Okay? There you go. That's your homework.
Oh, miss, I have a question for the last question.
Okay, give me some time. Okay, what's your question?
So for the result, are we just going to write limit x close to 0 and the x squared, like 1 over x squared equal positive infinity?
Yes. Yes, that's all you need to write. Limit as x approaches 0 from the right is positive infinity. Okay, and the limit as x approaches 0 from the left of 1 over x squared is positive infinity.
Okay.
Yeah.
Yes.
Yeah, no problem. So another way, just to give you guys an idea to do this, would be if you're taking the limit from the right, then you know that you're going to be very, very, very close to 0, right? You're approaching from the right, and it's positive. So you can sub in, for example, 0.0001 and see what value it is. And then you can sub in on the other side, negative 0.0001 and see what value you get. And you'll notice that they will both be positive, and so you can conclude that they are both approaching positive infinity. It's because it's squared. And that's why it's not necessary. You should be able to look at this and say, this is always positive. And I know that we've got asymptotes here. So really, it's a good practice to do it through analysis rather than rely on subbing in numbers. Right? Yeah. 0 infinity. There is absolutely no point on this vertical asymptote at all. No, it's a vertical asymptote. So the vertical asymptote is the break. There's no hole, the vertical asymptote. That's the break in this function. They're both approaching positive infinity. They're not going to meet. These two are not going to ever meet. They're on opposite sides of the asymptote. So from the right and from the left.
Oh, that's way to work, or use this way. So like, in previous example, that you have like x, and then maybe x equals 2 or x equals 2,
Yes.
positive.
Yeah, so that's what the right.
Oh, that's what's right over the.
Right or left. That plus and that minus sign there is for the right and for the left.
One over 2.
Yeah, no, that's okay. Are there any other questions? Okay, so let's move on to 1.5. Properties of limits. Okay. Given f of x and g of x have limits that exist and c is any constant. So what we're saying is we're assuming that, so these properties hold where f of x and g of x have limits that exist. Okay? All right. The limit of k as x approaches a is equal to k. Let's talk about what that means. So if you have the limit of k, the function is this. So your function is just y equals k. So that just means it's a horizontal line going through k. So if you have the limit as x approaches any value, doesn't matter what it is, it's always just going to equal k, whatever number that is. Okay? So, for example, if you guys want a number example, here I have 1, 2, 3, 4. So this would be the horizontal line y equals 4. So this would look like this. The limit as x approaches, and it can be anything. It can be 7 of 4. That's what it's going to look like. You're going to have to evaluate that limit. So it's going to say the limit as x approaches 7 of 4. But that's just a horizontal line. So we know that the height of that function is always just 4. And so the limit is just going to equal 4. Okay? So when evaluating constants, just keep in mind it's always a horizontal line, and so it's always just going to equal 4. Okay? The limit as x approaches a of x is equal to a. So what? So again, this is your function, and your function is y equals x. Well, the function y equals x means x and y are the same. So your points on this graph are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, a. Whatever x is, y is the same. And so it's just going to always equal whatever that value that you're approaching. Okay, so again, you want to do an example. Let's say the limit as x approaches -2 of x is just going to equal -2. And you can see that even just by plugging it in, yeah? Number 3. These are two properties put together. Okay, guys? Two properties put together. So, the limit as x approaches a, when you're adding two functions, is the same thing as taking the limit of one of your functions and then adding it to the second. So, limit as x approaches a of f of x plus limit as x approaches a of g of x. Okay? It's the same thing. So you can separate your limits. And the same thing with subtraction. So if I have the limit of f at x minus g of x, so that's two separate functions, I can separate the limit. So here's an example here for you. It's the limit as x approaches a of x squared plus 1 in brackets plus x cubed. I can separate these two functions. And I can say, well, that's going to equal the same thing as the limit as x approaches a of x squared plus 1 plus the limit as x approaches a of x cubed. You're just separating the limit. You can do that with addition and subtraction. Yes. I can't hear you. What is? What is y double? But we're separating the functions. There's no two functions here. There's only one. We're talking about when you have a polynomial. If you have a polynomial, you can separate the functions. It's separate. You understand? I could have even added in an extra limit here for just one, and I would have 3. You see that? Okay, number 4. Now I have a constant multiplied by the function. So something like 4x squared, right? My function is x squared and I have a constant in front of it, 4x squared. I can now take that 4 out of the limit, evaluate the limit of x squared, and then just multiply by 4 again. Here I'm multiplying two functions together. When you're multiplying two functions together, again, you can take the limits separately. So for example, I have x multiplied by x squared plus 3x minus 5. So I can say the limit as x approaches a of x multiplied by the limit as x approaches a of x squared plus 3x minus 5. And I should have brackets here. Okay? Similarly, guys, if you're dividing, you have here, look, I have a rational function here. You can do the limits in the numerator and the denominator separately. Okay? Number 7, the limit as x approaches a of f at x to the exponent n. you can now take the limit of just f of x and then put it to the exponent n. Just be careful, guys. This only works when n is an integer. Okay, this only works when n is an integer. And the reason for that is one of the examples we saw. We saw when we have an exponent of a half, that's your root function, isn't it? Does it work there? Does that limit exist? No, you have to be careful. So it's only when n is an integer. Okay?
Real.
Integer. Because,
It's here, it's real.
no, change it. Integer. Yeah, we'll look at, we did already. We did one already. We did square root of x. Square root of x is an example where it's not an integer. Right? Square root of x is the same thing as x to the 1/2. So we saw that that was a special case. So just be careful. Now, the properties of limits. Really, for you guys, you don't need them. And the reason I say that is because the properties are used when you're proving. When you have to do a proof, you need those properties to help you prove something. But you guys are just evaluating limits. So you guys don't really need that. So what's going to happen here is, I might ask you one question on the test and say, prove using the property. Or evaluate, show all the properties, show every single property. But it's only going to be one. Okay? Because really, you're going to see, we're going to do this one using the properties, and it's kind of useless, right? Where this is powerful is when you're proving. That's where these properties are needed, okay? All right, so here, rewrite the first as an equivalent expression using all possible limit properties, then evaluate. So if I had to just evaluate this normally, I would just sub in 2, and I would get my answer nice and easy. And we have to show all the properties, so let's do it. Who can help me? What's one property that you want to use here? Sorry, I can't hear you. What are you mentioning now? Yeah, the fraction one. Sure. She wants to separate her numerator and her denominator. Perfect. One property done. Is there another property I can use? I gotta use them all. In order to get full marks, you gotta use them all.
The
Okay?
addition.
Yeah. Perfect. Look at the numerator. Look
The
at your property.
multiplication one.
No, try again. Look at what you have there. You have 3x. What's 3?
Constant one.
Constant one. There you go. Okay. Did we get them all? Yeah.
Exponent one.
Yeah, you guys got it. There you go. Now, we've shown every single one. I think we got them all, no? What do you guys think? I don't see any others. So we've shown all the properties. Now we want to evaluate. So I'm just gonna-
Why would we,
Sorry?
like, why are we doing this?
Because it's important to know the properties, because if you continue with calculus, you may be asked to do proofs. So in order to do a proof, you need to know the properties. Plus, it's good to know what the properties are, right? Since you are evaluating limits, you should know what's allowed and what's not allowed.
Miss, couldn't we do the multiplication like from the start, from the first step, to do like a reciprocal?
What do you want to do? Do you want to bring that x squared plus 2 and make it a -1? Is that what you mean?
No, I mean like the limit of 3x times the limit of 1 over x squared plus 2.
Oh, no, I wouldn't do that.
Okay.
I wouldn't even make it negative in this case, because that's essentially what you're doing, right? If you want to use multiplication, you want to make that exponent -1.
Yeah.
I wouldn't. Okay, so limit as x approaches 2. Now we want to evaluate. So all we have to do is sub in. So it's 3. And then when I evaluate the limit, I'm just subbing in 2. Right? It's just x. And then in my denominator, I'm just subbing in 2. And it's squared. And then here, it just equals 2 because it's a horizontal line. Remember, guys? It just equals 2. The limit of 2 is just 2. And so now, no, I didn't need this. Sorry, guys. I don't need this. I've taken the limit already. I don't need that. All right. So now,
Miss, it's 6.
oh, what's going on? What? Oh, sorry. I'm sorry, guys. I'm sleeping today. So do you see all these steps that we did? For nothing really, right? Because if you're just evaluating a limit, you just need to sub in. But you will be asked a question where you have to show that you know the property. Okay? It's important to know your property. Cool? All right. Example 2. Evaluate each of the following limits if possible. So now we don't need to do all the properties. We just need to do it. So can I sub in -1 here? What do you guys think? Can I sub in -1? Will it work?
No.
I can't. So what should I do? Which method?
Factor.
Yeah, factor. You're going to factor it. So everybody go ahead and factor it. Use your product and sum, or use your crisscross. Use whatever you want. Tell me what this factor is. One. The factors? What are the factors? Okay. And now, we cancel. We know there's a hole in this function if we had to graph it. And now we just sub in. And -2 plus 3. Yeah. Oh, not necessarily. Look what it says here. It's possible. It's possible. Some of them might not exist. Yes, please. You can't do it. It will be factorable, or you can't do it, right? You won't be given one, it's not possible to solve, right? You will not be given one where that is an option. It would be silly, right? What would be the point? Okay. Right, yes, you're right. Sometimes that is the answer, but this is not a case where you would find that, right? It doesn't. Okay, limit as x approaches 0 of 2 minus radical 4 plus x over f. Can I sub in 0? Can I sub in 0?
No.
Thank you. No, so what do I need to do? SM talking to me at the back, what do I need to do? Yeah, conjugate. So you guys tell me, what's the conjugate here? Yeah. Okay, whatever. Let's do to the numerator. I must do to the denominator. Okay, so who wants to do this for me? Anybody at home want to do this for me? How do I multiply this through? Who wants to do this for me? Is there anybody at home with me still? No, nobody?
Miss,
Yeah.
I can do it.
Thank you. Who is that?
Nicholas.
Thank you, Nicholas. Okay, go for it.
So the numerator, the first term multiplies to 4,
Beautiful.
and then minus, and then open bracket 4 plus x.
Amazing. If you miss the bracket, you're gonna get the wrong answer. It's a binomial. Make sure you include that bracket. Beautiful. Now, Nicholas, in my denominator, am I gonna expand through that x?
No.
No. Because the whole reason I'm doing this is to cancel it, right? So, you notice that in the numerator, you're left with 0 plus x. The x is canceled. And I'm just going to go ahead and take the limit. We're approaching 0, so you're going to find 0. I'm sorry. Oh, I'm looking sorry, negative x. And so here I'm left with, yeah. Miss B's not in the right headspace today. That's the whole reason we did this, right? The whole reason we said be careful of those brackets is to make sure to distribute that negative. Yes, very good. And here I have negative 1 over 2 plus radical 4 over, radical 4 plus 0, and so I have negative 1. Beautiful. Good. So now really emphasize why it's important to have those brackets, right? Very good. Any questions?
Yeah, miss.
Yeah.
Well, can you remind me, like, is the conjugate just like supposed to be positive or something? Or is it like the...
So for the conjugate, Regine, so you have a binomial. So here I have 2 minus radical 4 plus x. The two terms stay the same, just the middle sign changes. So because that's a minus, it becomes a plus. That's it.
So what was the reciprocal?
See? A minus b. So reciprocal. What's a reciprocal? So if I have 2 over 3, the reciprocal of 2 over 3.
I get it.
Okay? Was that Regine? Who am I speaking to?
Yeah, that was me. I get it.
Okay. All right. Recall, factoring a sum difference of cubes. So we already saw this in the preview. Here are your two formulas. If you have a difference of cubes, notice that here we've got a binomial with a subtraction sign. And then here we have a plus and a plus. Okay? Here, when it's a sum of cubes, here we have a plus b, and it's minus plus. The signs are alternating. Minus plus. Okay? So how do we do this? You take the cubed root of a, you take the cubed root of b, and you pretty much sub into this formula. So let's do an example. I have x cubed minus 8 over x minus 2. I want to find the limit as x approaches 2. So can I sub in 2? I cannot sub in 2. And so I need to factor. And we notice that this is a difference of cubes. So I take the cubed root of x cubed, which is x. And I take the cubed root of 8, which is 2. And I'm subtracting because it's a difference of 2. Now, I have x, and it has to be squared. And now I need a plus sign here, and I'm multiplying your two values together, which would be 2x. And then you take your b value, which is 2, and you square it. And now you can evaluate the limit. And you've got 4 times 3. Are there any questions? Okay, last example. The limit as x approaches 5 of the square root of x minus 5. So what do I do? I just sub in? No, remember it's a root. Whenever you see a root sign, don't sub in, because you're going to get the wrong answer. It's going to say 0, and that's incorrect. So, because it's a root function, it must be done by analysis. Right? How do I draw this function? It's been shifted to the right 5 units. I know that from this. And then it's just your regular root function. I don't need the exact points. There's no negatives in there. There's no horizontal transformation. There's no vertical transformation, right? So we're good. So now, what do you guys think? Does this limit exist? Good luck. Here, I'll put in the function.
Wait, so would there be a hole there?
No. The reason that it doesn't exist is because you don't have a road to follow to the left of 5. There's nothing here to follow. So I can't even approach from the left. So because I can't approach from the left, the limit does not exist. Remember what we said, left-hand limit has to equal right-hand limit. Well, I don't have a left-hand limit here. But
Right.
remember, if I take this exact same function and I now say the limit as x approaches 7, does that limit exist? If I say the limit as x approaches 7, it does. And it's whatever this value is, because I can follow this way and I can follow this way. So just be careful. It all depends on where the limit, what x is approaching, right? When you're taking your limit. Yeah.
So it's one function, so y is equal to 0 and x is any number from not less than 0. And if it's the given y, x is 0, that's equal to
But it's not necessarily the case. What if I translated this function up to a unit?
But we have also tried to find a limit and unit follows on function.
Yes, but yeah, that's what we said, right? So that basically any graph where you have a starting point, there's a place where it begins, there is no limit. But you can't say this one is equal to 0 because I can do this function in all different places and it's like a 0. Yeah. Yeah.
Your x has got so any number greater than
That's exactly it. Your x has to include any number where the actual graph is. It would be in this case greater than. So be careful because what if it's like this? Now all of a sudden it's the opposite, right?
Yeah, it depends on what you're.
That's right. And that's my point. My point is we can't really generalize, we need to analyze. It's all by analysis. So always draw a rough sketch when you're dealing with roots. Okay? Okay, guys, and that's the homework for this section. You're going to notice that I've included the review homework, just for those of you that want to get started on it. You will have time to work on review tomorrow. Tomorrow we're going to be doing 1.6 only, and the rest of the time in class is to do homework and work on review. Okay? Now let's make a decision. I want to know whether you guys want the test on Monday or Tuesday. So I guess I'll do a poll. Let me see, I've never done this before. Let me see if I can do this. I'm sorry? Yeah, see, there's a use for that function. Okay, so let's go to it. I've never done this before, so let's see. How does this work? Cool.
Guys, please don't ruin the weekend.
Start a poll. Ask the question. Oh, I love this. Test on Monday? Actually, let's do it. I'm gonna put yes or no. Monday, that's okay, Monday, Tuesday, you got it. So now what do? I launch it? Okay. Okay, hold on, let's do the most simple. Monday, Tuesday. I'm gonna, oh, yeah, you can do it there. Are you gonna do it there? Or you can do, yeah, do it there. Do it in the classroom. Go in the classroom. It just makes life easier. Sorry? Oh,
I'm so stressed out right now.
why you don't know what to
This
do?
is so cool.
This is cool. This is cool. Okay. you getting
All right,
there?
we won.
Yeah, you really did, because even if everyone didn't answer, it's enough. It's enough. Okay, guys, test Tuesday. That means I'm starting chapter 2 on Monday. Okay? So I'll put that in the calendar. Does everyone know how to access the calendar? I'll show you right now. So in the class work here section of the classroom, just go here. And then whatever I might put here, assignments, tests, whatever, this is where it will be. It is, whatever it will be there. Okay? So let's edit this, because I said chapter 1 test today or tomorrow. So let's change this to. Sorry, say that again? Yeah,
They're gonna be mostly,
it's gonna be both, combination of the two.
but you asked me if we can have notes or not,
Yes, it's gonna be open notebook, guys.
oh, we can have our notes on.
Yeah, open notebook. But guys, I'm gonna tell you this. If you're relying on your notebook to be searching for answers, you're not gonna finish. So make sure that you study. Okay, because I'm telling you right now, the multiple choice, it's literally 2 minutes per question. You're not gonna have time to go look into your notebook. It will cut off. It cuts off at a certain time, whether you finish answering the question or not. Okay? So, just a warning. Oh, another, oh yeah, I did tell you that already. And, okay. Also, guys, with Prep Anywhere, I can't guarantee that all the solutions are correct. Unfortunately, I'm hoping that they are, but I can't guarantee that. So if if you come across a solution that you think is off or whatever, just ask me and we'll look at it too. Okay? I can't guarantee that it's correct.
Miss,
Yes,
so our chapter 1 test is gonna be up from 1.1 to 1.7, did you say?
1.6. Only
1.6, okay.
Yeah.
Thank you.
1.1 to 1.6.
Miss,
Yeah.
so for analysis, do you have to show the graph as proof, or do you have to show the left and right hand limit as proof, or both?
For which one?
For any, I guess, if it requires analysis.
So if I say that it requires analysis, either will suffice, either a rough little sketch, or if you want to do it algebraically, that's okay too. They're both good, right? They both work, so it's up to you.
Okay, and how are you supposed to know to use analysis? Is it only specific types of graphs, like the root
Yeah.
function and the rational?
Yeah.
Sometimes.
And the step function. The step function.
Oh yeah. Okay. Thanks.
Yeah.
So
Yeah,
all the other ones you use just substitution or whatever.
Yeah, you got it.
And, okay. Thank you.
No problem. I'm trying to think, I think the only graph that you guys know of that you've been exposed to that has a starting point is the root function. So that's the only one that you need to worry about. And then the step functions, anything that has a break in it, right? So anything that has an asymptote, or a step function, 2 branches. You always have to check it. And just because there's a break in your function doesn't mean that the limit does not exist. We saw that, right? We saw it with asymptotes and we saw it with step functions. Sometimes they exist and sometimes they don't.
Miss.
Yeah?
So I don't know who you're talking to right now.
Okay, hold on, let TNE saying something, hold on, yes, TNE. Yes, right, to analyze, right, to analyze that, we need to analyze. Okay, Radine, what's up?
All right, so like I was kind of like falling behind because like I was doing the homework. So like I'm doing the homework now, I promise. But like I'm kind of confused on like just because I don't remember. You know, like the ones where it's like there's two functions and it's like
Step function.
connected with like a curly bracket or something.
Yeah, those are called step functions.
Yeah, what am I supposed to do with those?
You have to analyze them. So hold on, I'm looking for one. Like these.
Yeah.
Yeah, draw a rough sketch. Draw a rough sketch so that you can analyze. Another way to do it really, you can do a left-hand limit and a right-hand limit and sub in. So like for this one, for example, here 11C. If I have, if the limit is approaching a half, for example, right? Well, then I can sub in one and or a number really, really close to a half and see what happens, and then a number really, really close to negative a half and see what happens. And if the limits are not approaching the same value, then the limit does not exist. Or you can just sketch it and take a look. Either way.
Okay.
So, do you understand how to graph these?
No.
So you've got to graph each branch separately. So here, you've got y equals 4x. That's linear. So that's the line that has a y-intercept of 0, and then it has a slope of 4 over 1. So that's why there's that, see how there's parts of this graph that are crossed out?
Right, like the scribbled out.
Yeah, they're scribbled out, and that's because you use them to draw the graph. That's how we got that linear function there at the top, but it's only true when x is greater than a half, right? Greater than or equal to a half. So I erased it for whenever x was less than or equal to negative a half. I'm sorry, positive a half. I don't need it. And then you have 1 over x when x is less than a half. So we know what that function is. That function is a rational function, right? So we know what that function does. We've seen it, right? How can I explain it to you? It's got the vertical asymptote, it's got the horizontal asymptote, blah, 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 cross.
Right.
Yeah, so then you draw those, but you cross out wherever it's greater than a half, because it doesn't exist there.
And then what are you trying to do?
Well, I don't know this question exactly, but let's say that we were trying to see if the limit exists at 0, as x approaches 0, let's just say. Would the limit exist here as x approaches 0?
No.
No, because one branch is approaching positive infinity and the other one's approaching negative infinity. So it would not exist.
So what about the part where they touch, like the...
Do they touch? Okay, so that's a good question. So let's talk about
Oh, they don't touch, but
what
like
about at a half? Would that limit exist at a half? What do you think?
I'm guessing it doesn't touch because x is less than 1.5.
But if I were to follow with a road, if I were to take my car, you know that little car that I used in the lesson, and I were to follow this road, would it go to the same place?
Yes. No. Yes.
Therefore, the limit exists.
Okay. I get it.
Here, the left-hand limit equals the right-hand limit. They're going to the same spot. So here, yes, in fact, the limit does exist here. The limit does not exist at 0, but it does exist at a half.
Yeah, but for this, the lower, like for the rational function, or no, the, what's it called? The root function? It doesn't, it says like it's less than 1.5. So
Yeah,
wouldn't the y values be different?
Yeah, but remember with limits, it doesn't matter. It doesn't matter. No, it's not that the y values are different. Look, if you sub in a half, right?
Yeah.
You're left with still just 2. And 4 times a half is also 2. So these do actually meet.
Okay, I get it.
They have the same value, so they do actually meet. But remember, with limits, even if there's a hole, the limit exists. Sorry, I'm trying to look here. Even if there's a hole, the limit exists, right? Look.
Right.
But if I go on the road, it continues on both ends. We end up at the same spot. So this limit does in fact exist.
Okay.
Cool?
Thanks.
You're welcome. Oh, that reminds me, there's also a handout for you guys to do for 1.5, so I better post that now. So I'll do that right now, okay guys, and I'll give it to you guys in class.